Welcome back, everybody. High Tech Lab here. Today I have 4 CA180 cells on my bench. I have my Fluke 287 and my Fluke 116 multimeters here. I have my dummy load connected up to water, and currently these batteries are connected to my inverter that I used in its charge function to bring these up to charge. Now, in my previous video, I bottom balanced these to 3 volts and then connected them in parallel without a BMS. I charged these batteries up to the 3.8 volt one cell max that is suggested by the Calb manufacturer of these batteries, and the first cell to reach that 3.8 volt threshold was cell number 4. I have these labeled with little numbers on here, so 1, 2, 3, 4. So if I were to probe cell 4, now these I charged yesterday and they've been sitting overnight. I have 3.577 volts. Cell 3, I have 3.363 volts. Cell 2, I have 3.386 volts. And cell 1, I have 3.429 volts. Now, these, as I charged them, were nearly identical within 8 millivolts as I charged them, but then when they got to the end of their discharge curve, they ran up the ramp of that curve very rapidly, and cell number 4 was the first one to run up that ramp. That's why its voltage is a little higher. But these are brand new cells, and these are genuine Calb cells. They have the genuine caps, bus bars, all that good stuff. So today we're going to be capacity testing them, and the first thing I need to do is disconnect my inverter, and then I have a cable with Anderson connectors here that I can connect on. And then I have a circuit breaker shunt combo, so I can use the circuit breaker to start the test, and that is connected with some leads to my Fluke 287, and I'm going to use that meter. It's a logging multimeter, and I can log the amps going in and out of the battery, and in this case they're only going to be going out. And I have a 600 watt 12 volt DC heating element here that is cooled by the running water through it. And that's my load that I'm going to send the power into. Now, I'm not going to use an inverter because an inverter can introduce an AC harmonic into the test, and the batteries will react to that in a way that can skew the result of this test. So that's why I'm using a DC load. I'm going to measure a few voltage set points throughout the testing, and we can actually take our data from the Fluke 287 into Fluke View forms and calculate our actual energy expressed in terms of watt hours. So that'll be really cool. Now, my purpose here, this is a sample pack that I bought. It was about $1,000. And I'm evaluating these cells because my intentions are to go buy about 256 of these, 64 of them for my use, 16 of them for a friend, and then the remaining 176 cells approximately will be for sales. To get started with this capacity test, I need to hook on this Anderson connector and remove the inverter charger, and then I can begin running water and close this breaker and start the logging multimeter. So let's get started. Okay, so I am all hooked up and ready for my capacity test. I have my Anderson connector attached to the battery, and that runs into my Y adapter that has the shunt and circuit breaker that I talked about a moment ago. I have my Fluke 287 connected to the shunt, and it is ready to record. I have it set to make a 5-hour and 30-minute recording with a sample every 3 seconds. I have 87% memory available on this meter, so I should have plenty of storage to do this test. I'm going to go ahead and turn on the water to my test load. And now that we have water flowing, we're ready to begin the test. So I don't have a BMS on this battery pack, so I'm going to be carefully monitoring these cells, and I'm going to stop the test at 3 volts because it's really not recommended to go below 3 volts. Okay, so I'm ready to begin the capacity test. The first thing I'm going to do is start the recording on the Fluke 287. The first thing I'm going to probe is the terminal voltage on these batteries, and that currently is 13.89 volts. I'm going to start the test, and the meter is already recording. So I'm going to start at the beginning of sample 6, which is now. I immediately had 54.7 amps, and it's starting to drop. My battery voltage at sample 10 is 13.37 volts. That's going to be important because I'm going to collect these voltages throughout this test approximately every 100 samples and plug that into my Excel sheet so that I can calculate, based on the resistance of this heating element, what the energy stored within this battery is. So I'm going to let this run its course with the Fluke 287, continuing to log the data. Now I need to wait around because at 52 amps, if you figure these batteries are right around 200 amp hours, this test is going to take 4 hours. So I really need to find something to do while I carefully monitor this, because like I mentioned earlier, there's no BMS on here to shut this test off when the batteries are empty. And like I mentioned, I'm going to stop the test at 3 volts. Okay, so this test is underway quite a bit. We're currently drawing 52.16 amps, and I'm on sample 370. 5 hours and 11 minutes remaining time on the measurement. But what's very interesting is if I probe cell 4, I have 3.274 volts. Cell 3, 3.272. Oh, let me get a better connection. 3.272 volts. Cell 2, I have 3.272 volts. And cell 1, I have 3.271 volts. And I'll go back to cell 4 so we can see if there's any drift. I have 3.274 volts. So these batteries are all within 3 millivolts of each other. So once it was down that initial couple of percentage state of charge, they all came right back into that bottom balance measurement. So these are coming down exactly together, and I suspect throughout this discharge they're all going to come back down identically. I haven't touched these one bit since I started the test, and I've been manually recording a voltage reading across the pack every 250 samples, and they've all been 13.08 volts, and we've only barely dropped 0.01 volts now to 13.07 volts. So these are coming down really nicely. I'm super excited with the performance of these batteries, and my heating element is staying nice and cool in here thanks to the flow of running water. And I'll keep doing this test and let you guys know how it goes. So we're about 3.5 hours in, and throughout this test I've been collecting the voltages of the pack at different samples. So sample 4000, I just got 12.20 volts across the terminals of the battery, and that's correlating to the samples on my Fluke 287. So that was 12.2 volts, and I'm going to plug all these into my Excel sheet when I get there. So if I check cell 1, currently I have 3.029 volts and falling. Cell 2, 3.044 volts. Cell 3, 3.041 volts. And cell 4, 3.080 volts. So I'm getting really close to the 3 volt shutoff, which I'm actually considering going slightly past because I'm drawing a pretty heavy load, and it'll bounce back up as they rest for a minute. So I'm going to make a note of the sample when the first cell crosses below 3 volts, and we can make a comparison in Excel and see how much power is actually available on the bottom end of these batteries. So I'm probing through the cells, and it appears to me that cell 1 is the closest to 3 volts. I'm at 3.005 volts, and we're at sample 4070. And I will wait until it crosses exactly through 3 volts and note that down. Now I'm actually going to bring these batteries to 2.5 volts, which I would not recommend doing. That's a very, very low state of charge, and it really puts some abuse on these batteries. But they're new, they can kind of take it. I will be, affected for the life of these batteries. So we're at 2.999 volts, so sample 4081 is what I'm going to call the 3 volt reading. And these are going to fall really quick because the discharge curve is very steep, and I will actually be able to take this data from Fluke View Forms and show you guys how steep that curve truly is. So it was quite interesting. Cell 4 was the first cell to hit the 3.8 volt charging limit, and here on discharge currently it's at 3.058 compared to 3.001, 3.013, and 2.989. So it still came down at a higher voltage compared to the rest, and I'm going to try bottom balancing this pack again and do another capacity test later on and see if cell 4 is still the hot cell. It's quite interesting how some of these cells start to get a personality to them and run a little bit higher voltage. So we're starting to get quite low, really close to our 2.5 volt reading, and I want you guys to look at the reading on my Fluke 116. This is the voltage on cell 1, and I want you guys just to take note of how quickly that's falling off. That just reiterates my point that there's really not much capacity below the 3 volt rating, and it's really not worth the stress and wear and tear on these cells to bring them there. I'm going to go to the overall terminal voltage, and you can see I'm really dropping quite low. A lot of inverters would have already kicked out by now, so definitely not worth it to do this. Cell 4 is 2.813 volts and dropping. Cell 3 is 2.7 volts and dropping. Cell 2 is 2.7. Cell 1, 2.6. So yeah, very interesting how little capacity there is, but I'm going to collect my sample 4500 and plug that back into the form, and we'll see exactly what there is in terms of capacity, because now I actually have the data on this and can illustrate it graphically. So sample 4500, I have 10.75 volts, and I'm saving that onto my document on my phone. So I have all these different samples that I've collected throughout this process, and that's dropped about a volt since the last sample 4250. So it's falling off really quite quick. I'm going to stop when cell 1, which has been the lowest cell, it's at 2.5 volts. So it's dropping about a millivolt per second, and in the next 60 seconds I should be stopping. So far, I started this test at 1:42 p.m. and it is 5:28 p.m. So we're getting really close to the 4-hour mark, about 3 hours and 45 minutes. So cell 1 is just now crossed into 2.5 volts. I'm going to do a quick reading. Cell 2 is at 2.587, cell 3 is at 2.566, and cell 4 is at 2.688 volts. And my terminal voltage across this pack is 10.28 volts. I'm going to stop the test now. That is sample 4561, so I can stop recording on my Fluke 287. And now that the decline has stopped, I can actually breathe and slow down a little bit, because making sure I capture this exact moment was critical. Otherwise, you guys wouldn't have anything to watch. So now that these have all dropped to 2.5 volts, I can remove the data from my meter and plug into the computer, and the computer will show us everything we need to know. Okay, so here we are in Excel, and I've brought all the data in here and done some calculations. I'll go through all this here shortly. But if you take note, we made a sample every 3 seconds, took 4,563 samples. And if we look down here all the way to the bottom, you can see all the data plugged in from those samples. Now, I've manually entered here in column D, in the volts column, the samples that I've manually collected. And for example, at sample 100, I had 13.08 volts. And what I can do is, because of Ohm's law, I can divide the 13.08 volt reading by the 52.24 amps, and that gives me the resistance of my heating element. And this will be very precise because it includes the resistance of the test leads and whatnot, and this will be the total load on the battery. So I got about a 1/4 ohm load, which calculated back into Ohm's law gives us 683 watts at sample 100. Now this is going to drop a little bit, but what my point is this is very proportionate, and we can use this to calculate watt hours if we'd like. So up here at the top, I have Excel graphing the current curve. Now this is sample 1, this spike up here at the beginning, because it's only got part of that in there. It was like 38 amps, 31 amps on sample 8. And then you can see there's a small dip down in the very beginning, and then it is very, very flat of a curve, and then towards the end it really starts coming down steep, and you can imagine if this curve continued, it would dive down to practically nothing. And because we were using a resistive load and have a resistive element, the voltage curve is going to be very much identical to the current curve, because that resistor is a constant due to Ohm's law, blah, blah, blah. It's gonna match up pretty accurately. So I did all my math in amp hours because I was specifically measuring the amperage, but I can actually calculate based on the current curve and voltage curve the total amount of watt hours. But for the sake of making numbers easy, I'm going to go in amp hours because that's the rating that Calb gives us. So for the full test, I ran an average current of 50.78 amps, and I took my times here. First reading was at 13:42 hours and 27 seconds. Last reading was at 17 hours and 30 minutes and 13 seconds. So the total time elapsed in this test was 3 hours, 47 minutes and 46 seconds, which was a total of 13,666 seconds. If we calculate that into percentage of an hour, just to make life easy, it's 379% of an hour. And what we can then do is take that percentage multiplied by the average current, and that will give us the amp hours. And in this case, for the whole test, I got 192.775 amp hours. And keep in mind, these batteries are only rated for 180 amp hours. So in this test, it was far over that 180 amp hour figure, which is why I personally like these Calb cells, is simply because they go way beyond their spec. And the nice part about that is 5 years down the road, when these batteries have been cycling for quite a while, they'll still have their rated capacity, which will be very nice. Now, I advise many people not to go below 3 volts for their typical usage, and the reason being there's not very much capacity there. It puts a bunch of extra wear on the cell. So I noted the first sample that a cell was below 3 volts, and that was sample 4081. And since I have all this data in here, I can grab the data points after cell or sample 4081. And the average current for that, if you look up here at the top of the formula bar, I have the average calculated from sample C10 to sample C4083. So the average current from the start of the test until the first cell hit 3 volts was 51.38 amps. And I go through all this math here to calculate the percentage of an hour. But essentially I got 174.3 amp hours out of these batteries before they went below 3 volts. And that's still very close to their rated capacity. So you don't need to push them that far down to get their rated capacity. Like I keep saying, it just wears on the cells. And then taking the inverse of the math, so removing this from the equation, I have here the first sample below 3 volts was 4081 again. So from sample C4083 to C4567, my average current was 45.7 amps. And I do the same calculation on the time, blah, blah, blah. Total seconds was 1,452 seconds at an average current of 45.7 amps, which gave me 18.4 amp hours capacity below 3 volts per cell. And double checking my math, this plus this equals this, which is very close to the calculation here. But either way, yeah, pushing these cells below 3 volts only gave me 18.4 amp hours, which is 10% of the capacity of the battery, rated capacity. But the stress it's putting on those batteries, again, really not worth it. But that being said, I'm really excited that these cells are performing this way. And I'm going to go ahead and get my order together of these. Because I'm going to install these on my off-grid ranch, and I will have 64 of them there, as I mentioned earlier. But if you're looking at getting some of these cells, yeah, 192 amp hours on this test. And one slight flaw with this test, I did notice towards the end, these batteries were getting a little bit out of balance. So in a next test later on, I'm going to get a battery balancer on here and make sure these cells stay within balance as they discharge using a Deli Green QNNB active cell balancer. That way, you know, any discrepancies between cells are taken out of the equation. And I'll do a new capacity test, and they should all cross below that 3 volt reading at the same time, and we'll see how those balancers actually give some extra life into these cells and keep them from just running at different parts of their discharge curve. And again, keeping in mind, let's look at sample 4081 because this is very interesting. If we look on the graph here, you figure this is the 4,000 sample range, so we're a little past here. And if you line these up vertically, they're about the same. This is where you really start seeing the decline in this curve. And you can imagine that if I pushed these any harder below that 2.5 volt reading, it's very little compared to how flat the curve is on the other part of the test. And this could be, you know, just the same as in your solar setup. You don't need to operate on the decline of this curve because it's just putting wear. This is the wear region. So staying between that 10% discharged and 90% charged is really, you know, very, very flat, and it's going to give you the best life out of these batteries. So either way, that's the results. If you guys have any questions or want a copy of this data that I grabbed, I can make that available. You can just send me an email at info@currentconnected.com. And if you're interested in getting a hold of some of these cells, I'm going to look into some more of purchasing these and reselling them here in the US on the East Coast. So you can also send me an email at info@currentconnected.com, and I can get you guys either sorted out in the US with buying some from me that I've already imported, or if you're outside of the US, I can get you directly in contact with a distributor that should be able to get them to you. Other than that, guys, hope you guys learned something today. Have a great day, and I'll see you in the next video.